Hi, Astronomy. This is Mr. Janowski. This is the second part of the Chapter 5 slides. So before we did the do now, we actually started with a Kahoot. So I'll put a link to the Kahoot in the description to this video. Then we started with this. What are the two main advantages of a telescope over the human eye? What are the two main advantages a telescope has over the human eye? Okay, that's better. More light gathering power. It makes faint things brighter, and more resolving power. It makes things that are very close together and impossible for your eye to distinguish. It makes them sharper, resolvable. You can tell the difference between things that are really close together. Second question: what type of telescope uses a lens as its primary optic? That would be a refracting telescope or refractor. And what kind uses a mirror as its primary optic? That's a reflecting telescope or a reflector. So all of the professional telescopes now are reflectors. They don't use refractors anymore. And there are slides that explain why. So what type of reflectors are these? The one on the left where the light comes down, hits a primary mirror, and then is imaged right here. That is called a prime focus telescope. This middle type, light comes in, hits the primary mirror, goes up to a secondary mirror, and then is sent down through a donut hole in your primary mirror, and then you image it down here. That's called a Cassegrain focus telescope. And this last type, where the light comes in, hits the primary, goes to the secondary, is kicked out the side, and you make your image on the side of the telescope, that's a Newtonian focus telescope. So I've said this before, but if you go to the telescope store, if you don't have much money, they will sell you a refracting telescope. Those are the cheap ones. If you've got a little more money, they will sell you a Newtonian focus one. This is the kind you can spend, up to a couple $1,000s on. If you're a professional astronomer, the big telescope at the observatory is going to be some variation of the Cassegrain focus design. And prime focus, this is mostly like radio telescopes. They operate this way. So differences between refractors and reflectors. Refractors, it's difficult and expensive to manufacture very big lenses like this. Now, it's also difficult and expensive to make very big mirrors, but it's relatively easier and cheaper. So you can make bigger mirrors easier and cheaper than you could make giant lenses. So lenses must be supported at their edges so they sag. You can't support a lens in the back, the center part of the lens. You can't keep it from sagging because, the light needs to get through the center part of the lens. Whereas if you have a mirror, you can support it all along the back. So there's ways to defeat this sagging problem. It is still a problem, but you can defeat it with active optics. So refractors suffer from dispersion and therefore chromatic aberration. So different wavelengths of light get bent by different amounts on hitting the glass and then going from the glass to the air again. That causes the different colors not to focus at the same place. So you get this chromatic aberration. Whereas if you have a mirror and it's silvered on the front side, silvered, it could be aluminum, but generally you would say silvered, you don't have this dispersion problem. All the light hits the mirror, comes out, focuses at the same place. Now, the fourth point, refractors absorb short wavelength light. The glass blocks the UV light. It kind of eats up the UV light. So that's no good for doing UV astronomy, obviously. Whereas mirrors don't have that problem. So they're more versatile. So last time, in the first part of the slides, we talked about light gathering power and how that worked. This part is mostly about resolving power. So start here. This image really should be flipped, but this is the way it was in the textbook. If you're looking at car headlights that are very far away, the headlights may be so close together that you can't tell that they're actually two separate headlights. So yeah, in this image, you can't really tell that they're two. As the car starts to get closer, your eye can distinguish the difference. And once it's close enough, you can definitely tell. So this is what resolving power is. Your ability to discern very fine detail. That's resolving power. So these are car headlights. Similar idea going on here with two very closely placed stars. So start again all the way on the right. If your stars are too close together, the light from them is just going to blend together and you'll only get an image of one star. So why does it look like a bullseye with another ring? More on that in a bit. As the stars are further apart, I mean, obviously you're looking at separate stars now, But if the stars are far enough apart, you can kind of make out that they're two stars. And once they're a certain distance away, their light is still kind of mixing together, but it's clear that these are two separate stars. So that's what these images and these graphs are. Now, unfortunately, you always get this mixing of light because of the wave nature of light. Light, when it goes through an aperture or off of a telescope mirror or whatever it is, you're going to get some diffraction. So diffraction is the bending of the path of light as it passes through an opening, such as the aperture of a telescope or around an object. So the light coming in here, left to right, all smooth and very planar, we would say. But once it goes through this aperture, it starts to bend. And that bending is not good. So we now have these curved wavefronts. So the resolving power of a telescope is fundamentally limited by diffraction due to the wave nature of light. So this isn't a problem of your lenses or your mirrors not being perfect enough. Even if your lenses and mirrors were absolutely perfect, and even if the atmosphere caused no distortion whatsoever, your telescope would still be limited by diffraction. It's called diffraction limited optics. And there's no way around that. That's just the wave nature of light. If your telescope is of a finite size, there is going to be some limit to the detail it can resolve. So diffraction causes a point source of light to be imaged as a bright central region surrounded by lighter concentric circles. This picture right here. So this pattern is called an Airy Disc. Now, this bigger picture to the left is showing you where the Airy Disc actually comes from. Don't worry about the nuts and bolts of this. It doesn't matter for high school level astronomy. If you become a professional astronomer, you'll have to learn all about this. But at this level, just know that it happens. This is what diffraction gives you, these Airy discs. And this image here on the right, I'm pretty sure I remember this is from Hubble. And they purposely overexposed this star to show you, the Airy disk pattern that you get. So, yeah, this here in the middle is one star. All of this other light around it, ignore the diffraction spikes. That is, it's also diffraction, but it's a different kind of phenomenon. It's the same phenomenon causing a different thing. Ignore the spikes, ignore the X pattern. Just look at the concentric circles going around. Even Hubble, as nice as it is diffraction limited. So you can't, like, this detail here, these concentric circles, it's not actually there. That's just an imaging artifact due to diffraction. And this pattern is called an Airy disk. So small telescope apertures lead to a lot of diffraction. So here's your light coming in, goes through a small aperture. You get a lot of bending. You get this. If you have a larger aperture telescope, so perhaps this is your lens, perhaps this is the size of your mirror, you still get diffraction, but you get less of it. And we have a formula here that relates, what does it relate? Capital D, the diameter of your telescope, measured in centimeters, to lambda, the wavelength of light being used, the light you're imaging, in units of nanometers, and alpha, which is an angle. It's the angular distance between your objects, measured in arc seconds. And remember, 1 arc second is 1/3600th of a degree. Why 3600th? It's because of the Babylonians. They like 60, and 60 times 60 is 3600. That's why we do angles weird. Anyhow, the way this formula works, alpha is the smallest angle that you can resolve, the smallest angular distance between your two objects. And you want this alpha to be as small as possible. If this number is very small, that means you can resolve two objects that are really close together as separate objects. So the way that works is if D is bigger, the diameter of your telescope is bigger, you can resolve a smaller angular distance, which is what you want. So how does the resolving power of the 8 mm pupil of the human eye in dim light compare to that of an 8-meter telescope? Assume that both are observing light with a wavelength of 500 nanometers. So you've got to pick just one wavelength. So this is a wavelength in the middle of the visible spectrum. So what you do is you take the bottom one of these formulas. So this is alpha. This is the smallest angle that your eye can resolve. So alpha sub I. You plug in your numbers, and it turns out the smallest angle that your eye can resolve is 12.5 arc seconds. So what that means is if you're looking at two objects and they're separated by less than 12.5 arc seconds, your naked eye can't tell that they're separate objects. They're just too close together. If you use the same formula, but this time for D, we're plugging in the 8-meter diameter of the telescope. 8 meters is 800 centimeters. you get a much smaller angle, 0.0125 arc seconds apart. So with your eye, 12.5 arc seconds, that's the smallest one you can resolve. With this giant telescope, 0.0125 arc seconds. So what that means is the telescope that has 1,000 times the diameter of your eye can resolve things that are 1,000 times smaller. So resolving power is directly related to the diameter of the thing that's doing the imaging. How does light gathering power compare? Well, remember from the first part, light gathering power is related to the area of the thing, and the area is proportional to either the radius squared or the diameter squared. So light gathering power, yeah, it goes as diameter squared. So if your telescope has 1,000 times the diameter, it has 1,000 squared, aka 1,000,000 times the light gathering power. So its resolving power, it's 1,000 times bigger, is 1,000 times better. Light gathering power, if it's 1,000 times bigger, is 1,000,000 times better because light gathering power has diameter squared, and resolving power just has diameter. So to review, what are the two main advantages that a telescope has over your eye? Well, last time we talked about it having more light gathering power. Today we talked about it having more resolving power. Now, what is the name of this pattern we're seeing over here? That is an Airy disc, named after George Airy. And what causes Airy discs and diffraction limited optics? Well, there it is. It's diffraction. Diffraction is what causes diffraction limited optics. Yeah, diffraction gives you Airy discs. So, how does a telescope's light gathering power, which is what we talked about in the previous class, relate to its diameter? Light gathering power is directly related to the diameter squared. The reason for this is that area of a circle is pi r squared, or pi times the quantity 1/2 diameter squared. Yeah. So light gathering power has d squared. How about its resolving power? Its resolving power just goes as d. So think of the bottom one, alpha, the smallest angle you can resolve, is ultimately related to 1 over the diameter. So if diameter starts to get big, alpha starts to get small. Um, Small alpha is what you want. Small alpha is resolving power. Therefore, resolving power is proportional to diameter. And that's it for the second part of the slides. Hopefully you found that helpful.